Hello, I am Camillus. Welcome to today's lab. Today we are going to treat consolidation, and it's actually one-dimensional consolidation. So firstly, I'd like to give the difference between compaction and consolidation, since last week we treated compaction. So last week we said that compaction is actually the expulsion of air, voids from the sand particles to increase the density. However, in consolidation, we are trying to expel the water from it. And mostly these affect clays because clays have low hydraulic conductivity. So with time, the loading settles in a very long time. So we try to estimate how much time it takes in order to estimate that. So moving on to the objectives for today. Firstly, the first objective is to plot graphs of deformation against log time and also deformation against square root of time. And basically, these graphs are just going to help us to estimate the various coefficients, for instance, the coefficient of consolidation. And that leads us to the second objective. And then this coefficient of consolidation is just helping us to estimate the rate at which the consolidation occurs. Now, for the third point, that's to plot a graph of void ratio versus consolidation pressure. And as you can see on the left side over here, this graph of void ratio against the consolidation pressure helps us to estimate the various coefficients. And that brings us to the fourth point, and those coefficients are the compression coefficient, that's the CC, the recompression coefficient, that's the CS or the CR. It's CS because sometimes it's actually swelling, and then the preconsolidation pressure. Now, the CC or the compression coefficient simply helps us to estimate the settlement that occurs in normally consolidated clays. And then for the CS or CR, it helps us to estimate the settlement that occurs in overly consolidated clays. Now, you may want to ask, what's the difference between the two? So for normally consolidated clay, it means that the pressure it is enduring now is the highest it has ever endured in its lifetime. However, for the overly consolidated clay, what it's experiencing now is less than the maximum pressure it has endured in the past. Okay, all right. So let me go straight to my fifth point. But before I do that, I would like to talk about the preconsolidation pressure. And then preconsolidation pressure is simply the maximum past pressure that that soil or that sample or that clay has endured in the past. Now, let's go to the fifth point. The fifth point simply asks us to be able to understand the drainage height, D. Now, to illustrate that quickly, I'll move on to this diagram over here. And this is my specimen right here. This is my specimen. And these two are what we call the porous stones. They are porous stones because when we set up the sample, we expect the expulsion of water to occur through the porous stones. Now, we have two types of setup. We have the one-way drainage and the two-way drainage. In this lab, however, we are going to treat the two-way drainage. Now, the reason why it's called two-way drainage in this sense is because unlike the one-way drainage, which I'll draw right now, so this is my one-way drainage, which means that the porous stone is placed on only one side of the sample. It means if I have a water particle over here that wants to be expelled out, it has to travel all the way to the top to leave out of the sample. So it's one way. In that case, the highest drainage height would be the whole length, which means that if a particle is here, it cannot come out through this side, but rather through the other side. So it's the drainage height should be the H, the total height of this. That becomes D. However, what we are using in this lab is the two-way drainage, which means that I'm having two porous stones, one at the top, one at the bottom. So like I was saying, so we have one at the top and the bottom. So what happens is that your highest distance of drainage for water particle to travel will become half the height of the whole sample, in which case my drainage height, which is D, becomes H divided by 2, where H stands for the height of the sample. So like I said, in this lab, our drainage height becomes H divided by 2. Alright, so welcome to the practical section of the consolidation, and now I'm going to show the apparatus that we are going to use in this test. And this is our consolidation cell in which most of the setup will be. This is my water that I will soon be saturating the porous stone inside. And then this is the porous stone. These two are the porous stones. Like I mentioned, we are going to do two-way drainage, and that is why we need two porous stones. One we place at the bottom of the sample, the other we place on top of it. And these are my two filter papers. Usually these will be in contact with the sample. And then as you can see, this is my wire saw, which I'll be using very soon to trim the sample right here. And then this is my caliper that I'll be using to measure the specimen. So I'm going to take the dimensions of the ring because the sample actually takes the form of the ring. So that will help us calculate the volume of the sample we are using. So firstly, I would like to take the height of this. Okay. All right. So I'll continue to take the inside diameter of the ring. So, like I mentioned, I'm going to saturate the porous stones with the water. And this is necessary in order to facilitate the movement of water through it. And then I'll go ahead to saturate my filter papers as well. So now I'm about to trim my sample, and this is the ring that I'll use as a guide to do that. So firstly, I'll just gauge it, and then make sure that's well aligned. Then I'll press it into it. Then after some time, I'll trim off these edges and continue pressing it to be flush with the top. So now, as you can see, I'll have to trim these edges off and continue with the process. Trimming, trimming. So now I'm about to trim the excess of the protruding clay. I want to trim it flush with the ring. Alrighty. So now I'm about to set up a sample, and this is our final sample. As you can see, it has been trimmed flush with the ring. So firstly, I take my saturated filter paper and I place it such that it doesn't overlap with the ring. Alright, so that's the perfect one. Now I repeat the same procedure for the top. Alright, then the next step is to place the larger porous stone at the bottom of the cell. So I go ahead and I do that. Then I go ahead and I put a sample on the top of the porous stone. And I go ahead and I place the porous stone on top of it. Then I close it. And as you can see, it fits well. The next thing to do is to use the screw or the nuts in this case. And once that is done, I assemble it. And done. I have my setup. Okay, so this is our GeoJack instrument that we use to perform the consolidation test. And this is the deformation sensor. Actually, as this thing settles, or as the settlement goes on, the displacement is actually measured by a deformation sensor. And this is the load cell of 2,000 pounds. And this is what applies the pressure needed for the water to be expelled out of the sample. So what I will do now is that I will place my setup under the load cell. And I will make sure I sit the load onto the setup. Okay, so now I will place my deformation sensor on the knob. Alright, and one thing to note is that since these things are going to measure displacement, it's important to calibrate it and then re-zero it to make sure that any displacement that is measured or any load is actually starting from the initial point. Alright, so as can be seen on the screen, that is the loading schedule of 125, 250, 500, and so on and so forth. So the next item to do is to saturate the sample, since this is done in a saturated environment. So I'll go ahead, saturate this sample. Okay. So my sample is saturated. So I now go ahead and start my test. Okay, so now that we've saturated the sample, we've started the test, I'll come back after 24 hours to take the reading. And since it's an instrumented test, the data will already be ready to the machine, and I'll use the data to plot my graphs and be able to get the result I want. So thank you so much for being part of this lab session. Once again, that was one-dimensional consolidation.